Here's an example of an integration method called partial fractions. So here you have an integral, and we could probably multiply that together, complete the square, and use some other method out of the table, but we want to teach how to do partial fractions here. So what partial fractions is to break up this product as an addition of two fractions. So you take the whole thing, and the idea is to write it as a sum of fractions. So what do we need to do is to find out what this A and what this B is going to be. And there's more advanced techniques as the examples get a little bit more complicated. So you start off with this. What you do, you set it up. You set up the equation, and then you multiply both sides by the LCD, which is x minus 1 times x minus 2 on both sides, here and here, and you distribute in, and you cancel out this, and you're going to end up with 1 equals this. And the idea is that coefficients of like terms on each side of the equation must be equal. After you've simplified this into a polynomial, and after you simplify the left side into a polynomial, the like term coefficients must be equal on both sides. So let's see. So we take the right hand side, because the left hand side is already simplified, and we distributed the A and the B into here, and we get to the statement. Now we're getting the coefficients grouped on the x term and on the constant term and on any other degree terms there might have been, and we're going to do that on the left and the right and then match it up. So right now you realize on the left you just really have 0x plus 1 sitting there. There isn't any x term. So since there's no x term on the left and there's an x term on the right, this a plus b must equal the 0 from the 0x plus 1 that's there. So a plus b is 0. And the constant term of 1 has to equal this constant term. That's where you get this from. Okay, so there's your two equations, two equations, two unknowns. You can solve that by any kind of method. I did it by adding equations here, but you could use a matrix method, a calculator method, put them in the Wolfram alpha, anything would work. Get this A here, plug it back in the other equation and get the B, and then follow the formulation that you had, which is right here, and stick in the A and put in the B, and there's your partial fraction decomposition. You have taken your fraction that has a multiplied denominator and changed it into addition of two fractions, and here's the check just to make sure that it's done right. If you take the sum of the two fractions and glue them back together with algebra, you do obtain the original fraction. So then to solve the integral, of course this integral does appear in the table form, so that's one way to do it. But with partial fractions, we just found out that this fraction here can be broken up into these two. You handle each of them separately, and because there's a 1x on each one, the substitution method really isn't necessary. You just go ahead straight to the answer, and here it is. And of course that agrees with the table that this form, which is what we had, was equal to this. And if you put all the a's and b's in, that's exactly what you're going to get. Another example of partial fractions is you have this denominator and you factor it, you get this, but this time we have a numerator, so that's a little bit different. but we still follow the same procedure. You'll realize later that when you have non-repeated factors in the denominator, you lay them out as one denominator here and the other one here. If you had repeated factors down there in the denominator, you're going to have to do a slightly different procedure, but we'll get to that. So same procedure, we multiply both sides by the LCD, and then that produces this equation. Grouping the terms together, now you see you have this. So now you realize that the a plus b is the coefficient of the x. That must match up to the 2, and the 1 must match up to the negative a. So that's the way you're going to do it. Here's your two equations, and solve. B equals 3, plug that back into one of the equations, put the 3 in, and a equals negative 1. So here's your partial fraction decomposition right here. And so this original integral would equal the integral, or sum of these two. And again, since it's a 1x here and a 1x there, you can go straight away to the, so we can just go ahead and integrate these, and of course you get this final answer. And that form actually is in the table, and it could be, if you put all the right C and D and A and B in there, and you put everything in there, it'll come out exactly equal to what our answer was.